Okay, so yeah, I have a bit of a recap part, which is this black part, and then some further thoughts and ideas that build on that. We don't have to go too deep into the recap part, but I thought it would be useful, especially also for unials. And I felt like in the past weeks we had several clarifying ideas. Most of them Jeff talked about over the past weeks around three bigger topics, which is attention, causality, and the role of the hippocampus. Um, yeah, do you guys want me to go over those again, or just that might be
I,
useful, maybe.
I would,
Okay.
Yeah.
even though I had came up with a lot of ideas, I can't remember them. So
Yeah, it might also be good to just clarify that I'm understanding them the same way and we're kind of on the same page on those. So, yeah, so around attention, one of the big reframings or thoughts. I mean, I know we brought up a lot of those before, but again, it feels like it's just kind of snapping into place now. So that, yeah, we always pay attention to one area in 3D space at a time. And so I think this is part of what you also wrote in the text over on the side, Jeff, that first we try to recognize the largest object in that space. If that's not possible, narrow the attention to a smaller area to recognize a subcomponent on that object. And then once the smallest recognizable feature is found, at the worst case scenario, it would just be the sensory input. Then we learn a compositional model at the next hierarchical level up of that object. Like kind of the thing, like you look at the word first, and then if you don't recognize the word, you focus your attention on the individual letters. And if you don't recognize the letters, you look at the individual strokes, and then you build a model of those. That makes sense?
yes,
Okay, and then second, the attended region is broadcast globally. So I thought this was kind of a nice idea that I think we talked about last week that solves a couple of issues that came up over the past years, which is well, here I put a bit of a question mark. So this attentional gating of input and voting, the idea that columns that get input from a region that isn't currently attended to in 3D space won't process this input or participate in voting. Basically kind of, yeah, gating our attention really to that specific region in space. Put a question mark there because a bit later on I talk about something that might require that, but
well, we talked about this, that the regions that are not in the intended space could potentially be learning, even though they're not actually processing input. That perhaps they could be learning the same things the other ones are learning. That idea is thrown out.
yeah.
I don't know if that's. I don't want to go down there.
Yeah, so that's the second point.
Um,
So I took out a 8C. Hippocampal complex will lay down a temporary model of what is sensed at those locations that attended to could be low-level features or complex compositional objects, depending on what's being recognized. But then the next point being, I think what you're referring to, Jeff, the attended location in 3D space can be used for morphology-based learning and inference in columns that don't receive input. So basically the idea is like when someone's drawing on your back, the locations at which you attend on your back change over time. And those attended locations on your back can be broadcast globally. And so since they're broadcast globally, they could be used to invoke relative locations in visual models, for example, and recognize basic morphology like shapes in visual cortex and invoke that kind of mental image in your head. And so that would mean that not all models need to be learned everywhere. So there's less need for model transfer between columns. So for example, the back of your hand doesn't need a model of a mug. It can just rely on columns connected to other patches that have models of mugs. Basically, if I draw a mug on your hand, you can kind of visualize the attended locations in space, or your visual cortex column that has a model of a mug gets those attended locations in space and can use those to infer the mug. If that makes sense.
right. So that we don't have a model of the mug in the patch of your hand, but the hand can invoke the model of the mug in the visual cortex through the common space.
Exactly. Yeah.
Yeah,
Um,
interesting. And did you have any discussion already on like anatomically what this kind of broadcast of the location corresponds to, or
No.
is it kind of like the shared
I had the,
egocentric coordinate system, or
well, I'll let everyone else speak. I'll speak first. I have no idea how this works, but it seems like it's happening. So maybe someone else knows how it would work.
yeah,
yeah, it would be some whatever is doing attention
A
to a region
colostrum.
in space.
yeah.
A colostrum. Throw it in there. There is. It just seems it has to occur. I mean, it's funny because it would be easy to do in Monty, right? We could
Yeah,
Right.
program this.
It's also interesting because part of me feels like it's a location. Like when we talk about attention, that definitely feels like a location in 3D space. But when you talk about the example of the drawing on the back, that almost feels like a global broadcast of a movement. Like it's more like all the columns are being told, yeah, now we're moving down a bit. Now we're moving left a bit. And they're using that
Uh,
information.
maybe. Uh, well, I
And
think
then and then maybe that's
don't.
easier to share. I don't know, because
Well,
then
not
it's
be careful there because when you draw on someone's back, you don't have the ability to draw a line. You don't have the ability to impress a line upon the back. The sensors don't even work very well like that. So we actually we're drawing it and we're moving. So there's movement of your finger when you're doing it. It's so I'm just saying. And just be
that's
careful
kind
that.
of what I mean. Like, what is the location in that case? It feels like
I
it's more of
think,
a movement.
but
But
for example, if you just dot on your hand, like you dot a triangle on your hand, there isn't really movement itself. It's just some relative locations on your skin.
right, right.
I think
Don't confuse.
that would be really hard to do
Well,
to
it's really hard to do that.
recognize and I mean you can still infer a movement from that, like which two dots were followed each other.
I don't know. I think if you did a dot, a dot picture on my back, it would be about the same difficulty as drawing on my back. Um,
The
Interesting.
next
I,
retreat is going to get really weird.
I think it depends what the spacing of these dots are, but yeah.
no,
Uh,
assuming they're close together, right?
right.
And it's not doesn't have to be an implied movement. Um,
So they could be in random order.
I think it's funny.
I think
This
your back has very bad sensors, so I'm trying to think about the palm of your
right,
hand, which has a bit higher sensory resolution.
right. It's very very bad in the back. I think it's something like you can't tell like 2 inches apart, you can't tell the difference or something like it's like it's really an inch or something. It's pretty big. Um, well, I think let's not get. I want to go through Vivian's all of her stuff, so I think we can leave it.
Yeah.
Yeah, you said the open. Is that what the open question says? I don't know.
Yeah, I
Um,
just wrote down what part of anatomy is responsible for attending to region in 3D space and broadcasting this.
there's an interesting twist on this question. I've thought about a lot. Is it a 3D region in space? Is it a point? And you could say, oh, well, grid cells would encode a point, right? There's a location in space, but it feels like if uh, and so for example, what if I hear a sound a sudden sound in the bushes behind me? I would have a point in space where I heard that sound, and I quickly look to see what was there. It's dangerous. However, if I'm looking at I'm reading text, and there's this odd symbol in the text. It's not like at that point the oddness is detected over some area or region. It feels like I'm attending to the entire thing, not a point. It's more like, or it's like here's the edge of this thing. It's bounded by all these mispredictions. There's a bunch of mispredictions, and those mispredictions defined a volume in space. So the question is it a point, or I keep coming back to like a 3D volume in space that times could look like a point. But it's an interesting question to think about, because if we talk about the mechanism, are we trying to specify a point, or are we trying to specify a boundary or region? I think it's a boundary or region that can at times look like a point, because we don't have any more data, like with the sound behind me. I may not have any volume data. It might be just a point. Of course, if the rustling occurred in multiple spots behind me, I think I would know that. and I would look, and I would attend to a larger area. You know, I have a sense of it. Is that a point sound or is that an aerial sound? Anyway, I think it's an area or
Yeah,
volume.
I wrote those down as
Yeah.
open questions. Which, yeah, I think don't really prevent us from thinking of these high-level ideas. They're mostly like lower-level anatomy and implementation
Right.
questions.
But I think it might make a difference if it's a volume. Like you have to be able to
Yeah.
think about how would I specify or how would I detect that. Anyway, all
Yeah.
right, good. This is good.
Yeah, I do agree. It seems to, right now, it seems to make most sense to think of it as a volume because we can then kind of narrow our attention to smaller areas and things like
Right.
that. So
Right.
at least that's how I've been thinking about it for this part now.
Me too.
Okay, so then, yeah, if there are no more questions around attention, I'd move on to causality, but yeah, if something's unclear, can talk more about this, no? Okay, so then causality, the kind of two main points I wrote down here was we can learn a causal model of like I'm in a state, there's an action or behavior that happens, and I predict to be in a different state. We could do this using the apical dendrites connecting to a broadcast signal in layer 1. And so columns would broadcast the current state, which they represent in layer 3, widely to layer 1 in other columns. And then receiving columns can use apical dendrites in layer 3 pyramidal cells to learn temporal causality between their state and the received broadcast signal. And that allows correlating spatially or conceptually distant percepts with each other if they are close together in time, like the switch on the wall with the light on the ceiling. That kind of capture what you talked about last week, Jeff?
Sounds good. Even if I didn't say this, it sounds good.
Yeah, I tried to kind of capture some of the parts here. Like I think that's mostly this arrow here, temporal causality.
Right.
And then second, the layer 1 causal context signal can represent a variety of things. This is maybe a bit extrapolating from what you talked about last week. So it could represent a behavior state, like the switch is flipped. It could represent a morphology state. It could represent an action that was taken, or it could represent a goal that's imagined. This is a bit what I suggested during the brainstorming week, that we could use the same mechanism to broadcast a goal and then associate like transitions from one state to another given a goal.
I think maybe I didn't understand that when you presented that the first time, but I think maybe you know I was saying the same thing. I was saying a goal is just it's a behavior that it's just an imagined behavior. It's like a behavior.
Yeah, I think we're talking about the same thing, just with different words. Yeah. Oh,
It's just,
thank you. Volume's gone.
Oh, is it my volume? You can hear me?
Oh, no, now I can hear you again.
Oh. Anyway, I was arguing that the goal is just it looks exactly like an actual behavior, but it hasn't been. But it's just the person sending it out knows that it's just imagined. It's like the light turning on. When the light turns on, that is a behavioral state. The transition from off to on, but the column that's observing the light turning on could send it out even if the light isn't turning on. It's just oh, I'm imagining it turning on, and then everyone else will treat it the same. So
Yeah.
I think that was the argument I had for that.
Yeah, and so basically the point I'm trying to make here is that the inputs to layer 1 can be pretty varied. The receiving column doesn't even really know whether this is an imagined behavior or a morphology state or an action taken. It just gets a bunch of input to layer 1 and it forms causal associations if those appear kind of temporally correlated in time. And the inputs can come from different regions, different modalities, or different levels in the hierarchy. Since those connections to layer 1 are pretty broad, you can learn a lot of different causal relationships.
Right. those things have to change right before the receiving column state changes. So it's not good enough to say, oh, there's a light switch on the wall. You know, the switch has to be changing. Or I'll leave it at that. I don't want to get into details about it. But
Yeah, I think, yeah, I mean, firstly, I like the idea of projecting this with kind of lateral projections in terms of kind of goals and causality and stuff. But yeah, I feel like there'd be a lot of interesting stuff to talk about. So maybe this would be a good one to return to next week so that, yeah, Vivian, there's time for your other stuff.
yeah, let's
Yeah. Yeah. Okay, cool. So that's good. Should I move on to the next topic?
sure.
Okay, so last part, role of the hippocampus, and I'll try to be brief because I think, Jeff, you just talked about most of these points. I'll just try to recap it, how I understood. So yeah, one, it rapidly lays down points of what is currently recognized at the intended location, and there represents the largest and most complex recognizable feature in that area. So if we recognize a complex compositional object at that location, that would be laid down at that location. If we don't recognize that thing, we've narrowed the attention more and more. And if we can't recognize anything, we might have to lay down like a direct sensory input feature at that location that's currently being sensed. And then, yeah, thinking of it kind of as a single cortical column with one reference frame active at a time, that, yeah, tries to recognize the compositional model of what we're currently exploring, for example, an environment in which movements are made, or a larger object that is being explored. And then once recognized, we can quickly lay down additional information like the current arrangement of objects on the table after we recognized our dining room. And then a temporary model can be used to invoke predicted models at lower levels in the hierarchy through top-down connections to make kind of more specific predictions or to interact with the world intelligently.
All right. So predictive models, both morphology models and presumably behavior models, right?
Yeah, right.
So I see the toaster on the counter, and then I can imagine what the toaster does.
Yeah. So kind
Good.
of like, oh, I predict I'm gonna see my cup over there because a few moments ago I looked there and I remember there was my cup. And so I invoked the cup model lower down in the hierarchy that actually models the details of the cup and knows what kind of sensory input it should expect.
Right.
And then inference can be extremely fast if we're receiving unique child object IDs. That's kind of what you said, Jeff, earlier. That the more and more unique those object IDs get, the quicker we can do inference without doing a lot of movements. So we rely more on the outputs of other columns, which are complex compositional object IDs, than on pure morphology. And that also means that the learned models can be sparse, as they can rely on few unique features, like the intersection that only stores a couple unique features to recognize it. And then the more detailed models of them are learned at lower regions.
That last point is very powerful. It means the capacity of a single column can be quite high.
Yeah, true. Yeah.
Which is also important, I think, when you think about what the hippocampus represents, which is like unique memories. You know, there's so many potential kind of, yeah, unique arrangements and things like that we do seem to have some kind of memory of, whereas that's much harder for kind of, or like we don't want to have that kind of amount of, yeah,
Right.
just for kind of generic objects, I guess is what I'm trying to say.
Basically, if an object is a set of features at locations, once you have complex features, you only have to store 2 or 3,
Right.
locations, and you're done. And so you don't use a lot of memory for that.
But just like, yeah, I guess like rooms, like if you go through in your head, you can imagine thousands of rooms that you've been in. It would take time, but all the different houses you've been in, all the different offices and things like that. And
maybe hundreds. I don't know about thousands, but
I think if you spent long enough, like going back to your school
maybe. But the
hospitals you've been in,
but
and
but
of
the
course it
point
wouldn't be a perfect representation, but you'd,
it
yeah,
was the
I don't
point.
know.
It was the point I made about the intersections earlier. Once you've identified one or two key things that define that space, the other ones you don't really have a memory of. It's like we went back to a room that, classroom you had before, and some details where the light switches on the wall changed or something. You wouldn't know that. It's just like, but you're in that room because there's a couple of unique things that really identify it. But the point is, if you only have to store, let's say, 3 pairings per room, the capacity of the system is huge. The capacity of grid cells to represent space is unlimited number of spaces they can represent. And there's an unlimited number of unique IDs you can have for child objects. So really, it's just the memory that's required to store the pairing between a child object and the reference frame. And that doesn't take a lot of synapses, but if you only have to store 3 of them, 4, few of them, then you can store thousands and thousands. You could recognize thousands of objects, no problem, in the same column.
Yeah. Yeah, I think that's right. That's a pretty important point and property. Okay, so is that all good? Should I move on to the further
Yeah,
thought?
let's go on.
Okay, cool. Niels, does that make sense to you too, or
Yeah, no, definitely.
been kind of pretty
You
brief?
just save yourself several weeks of work. You just come to this meeting.
Yeah, so I have 3 kind of further topics. One is around learning which actions to take. So kind of the other way around, instead of taking a state and an action or behavior and then predicting the next state, having a current state and a goal state, and then figuring out which action to take to transition between the two. And then 2 more that I'll get to. So for the learning which actions to take, what I'm proposing, or kind of try to propose during the brainstorming week, would be that we could use the exact same mechanism as outlined in this kind of causality model. So basically, instead of layer 3 pyramidal cells, we'd be looking at layer 5A pyramidal neurons that use their basal dendrites to pick up the current state an object is in, and then the apical dendrites pick up a goal state in layer 1. And once a specific reality goal combination is detected, they would fire, and since their axons go subcortically, that signal would then be interpreted there to figure out how to execute it. And the outputs from those layer 5A neurons would be interpreted as target poses in like a target location orientation in a common reference frame, for example, relative to the body. And then the subcortical motor system could figure out how to get there with whatever action space is available to it. So basically saying to go from state 1 to state 2, I need to go to this location in space and this orientation, and that gets sent subcortically by the layer 5A neurons. Or could, it's just a proposal. And then, so this is for the kind of motor output, but we still would need to figure out how to decompose goals into sub-goals and kind of have hierarchical action decomposition. And so for that, what I would propose is use exactly the same mechanism from here for causality. Basically, other layer 3 neurons could represent current state and goal state combinations. Again, apical dendrites picking up a goal state in layer 1, and then those neurons respond to a specific correlated current reality and goal combination. And then their output could then be broadcast widely to layer 1 in other columns again, where it would then be used in the same way, kind of just going down the hierarchy until we actually produce an action output subcortically. And again, the receiving column might not even actually know whether this is a goal state, an imagined reality, or if it's an actual reality or an action that was taken. It would just learn these associations Yeah, I don't know if that was confusing.
Yes, it was confusing, but it's very intriguing. I'm assuming. Well, I'm just going to assume that I'm not the only one who's confused. Oh, what happened to it?
Maybe if I can show an image.
Yeah, that might be helpful. Well, I was trying to pick apart the words in your sentences there, trying to understand what you meant by them. But
yeah, basically, this is the first part of what I was talking about, where we have a pyramidal neuron in layer 5 that picks up the current state that
current
its
state of
column
what?
represents.
Current state of what?
Current state of reality.
What do you mean it picks it up? Doesn't the whole column represent the current state?
Yeah.
So
whenever the column is in, I don't know, hinge state 1, this neuron receives input to its basal dendrites. And then when it
As
gets the
in
goal,
from projections from L2, L3 down to layer 5.
yeah, either that or from the location representation on that behavior.
So why would it be learning now? I mean, is it learn all the time? Is it just an alternate representation of the behavior of the state? When does it learn?
No, it learns to associate the current state of the object represented in that column with some context that comes into layer 1. And
Okay,
in this case, the context would be goal.
okay,
Same way
so
as this mechanism here.
so it's odd to think of this layer 5 cell learning the current state because it's part of the column that is the current state. I mean, layer 3 in this case is the current state. So why am I picking layer 5? I think you're trying to do some motor output or something.
Yeah, the only reason I put it in layer 5 is because that's where the subcortical motor output comes from.
Okay, so let's just divorce ourselves from this particular layer 5 dendrite things, but you've got a current state in the column.
Yeah, maybe this picture is capturing that part. So we have a current state, which is the stapler's open, and then layer 1 gets a goal, like an imagined state, which is the stapler's closed. And those get associated, and when those happen together, they would send an output to other columns that then figure out how to achieve that.
Well, what's its output in that case? It's basically saying, oh, the stapler's actually not open. I want it to be closed. So normally that cell in layer 3 would say, oh, the stapler is open or the stapler is closed. But now when I get this input on the table of dendrites, it's going to say, I want the stapler to be open or I want the stapler to be closed. Is that what you're saying there? It's just like an imagined. You're broadcasting. So at this point, you're using the layer 1 to say, okay, the same cells which normally tell me the stapler state, now those cells are now going to mean the desired stapler state, right?
Yeah.
Okay, so that's fine. That goes back to the same thing we were talking earlier. Like it's the same axons, the same neurons projecting, but we now know they're representing. At this point, no one else knows this, but at this point, it's like saying internally it says, oh, this is desired, so I'm going to send out the desired state as if it was real. Everyone else, I'm going to tell everyone else. Okay, so now all right, I'm following that one. Okay, so now we bump over to the behavioral model, and it's projecting up to layer 1, and the behavioral model now is seeing a signal that says, from its point of view, it's saying, oh, the hinge is in the closed state, because that's the goal, right? The goal is closed. The hinge is closed. That's I don't know if the hinge is closed or open, but but that's
Oh, I think your audio is out again.
Jeff, your audio went out for the past 5 seconds.
I don't know why. It sounds good for me, but I'm just trying to walk it through your.
So you got cut off after, I don't know if the hinge is in the open or closed state.
Okay. All right, so I'm looking at the behavioral model now, and it's getting that purple line, and so it interprets that purple line as either, oh, the hinge is open, or it represents hinge or open, hinge and close. The behavioral model doesn't know anything about this. It just says, okay, here's a pattern. It doesn't know if it's the real thing or it's an imagined thing. Maybe it would, but it doesn't. We haven't introduced that yet. So now the behavioral model layer 5 cell recognizes this thing and says, oh, it says, I don't know why I would have learned this. I'm trying to piece all the pieces together here. Viviane, it's not clear to me how this works.
Yeah, so basically, yeah, this is showing an image of when it's already been learned. Basically, it is learned whenever it gets this input to layer 1, which is I want the hinge to be closed. It has a hinge model of the hinge, and it's currently not matching that state. It's in a different, it's in the open state. And so that specific combination causes this neuron to fire and send a motor output, which then you would need to learn to interpret as apply pressure at this location.
There seems to be some problems, maybe, or I'm confused. For the behavioral model, in some sense, doesn't know about staplers. It knows this about movements of things. So for it to say it's like, oh, there's a thing that's moving up, hinge, it's a hinging behavior, like, you know. And so if it's looking at the stapler morphology model, it doesn't, on its own, that purple line between the morphology model and the, it doesn't seem to be the right connection. I don't want to like only learn this, you know, the behavior model has to somehow work with non-staplers, right? It can't be tied to the stapler.
Yeah, you would need the same neuron to fire for other morphology models as well that have a stapler behavior associated with it.
Yeah, but then the behavior model has to learn all these different objects that it could be applied to. It seems to be, I think, first of all, I like to say, I think this kind of diagram is the kind of diagram we need to be looking at. I'm just questioning the connections you're making. So I'm just trying to be like, okay, is that the connection?
Yeah.
Is that, you know?
Yeah, I guess the main kind of idea is to use the same mechanism we use to learn temporal causality, to learn, yeah, kind of the inverse model of which action to take to transition between states.
Yeah, I think I just don't. I think you are close. My first guess is it feels like this. There's maybe one more piece in there that you didn't show or something. It's like I don't think I can go right from the stapler state to the behavior. It feels like I need to go from. I don't know yet. I don't know. I'll just let it.
Yeah. Okay. Yeah, that's fine. We can come back to it or think about different solutions.
Right.
I'm actually more excited about these parts. So.
Oh, okay.
Yeah. So, as I was thinking about this stuff, I was thinking, yeah, this mechanism of learning state action function, kind of like the inverse model, is really quite limited because it means you can only perform actions after you've done it before and after you've learned those combinations. And that's clearly not all we can do. We can do totally new actions that we've never performed before. We can put the world into states it's never been in. And we can kind of make plans to do things we've never done before. And so I was thinking a lot about, okay, how can we plan novel actions and how can we execute novel actions and how can we figure out state transitions that we haven't done before? And of course, a big part of this is kind of the generalization capabilities we get from representing morphology and behavior models separately. So a lot of it also works with just, applying the hinge behavior to a novel object. So this might not be required for in that many situations. But still, I think there is a requirement to have kind of the ability to plan novel actions. And so I've been reading a bit more about kind of hippocampus, and unfortunately didn't get through everything before today, so there's still some gaps in my knowledge right now. But kind of one way I've seen it phrased is that it can function as a mental scratch pad. And I kind of like that phrasing. So it kind of relates to what we just talked about. So you can quickly lay down points in a current reference frame of the current temporary arrangement of objects. But then you can use this temporary model to activate models in the other columns through top-down connections, like predict the plate model at location X again, because I just looked there a moment ago and saw a plate. But then hippocampal complex can also use the temporary models to simulate future realities. That's the kind of preplay that's been observed before when they have mice in an environment and you see series of place cells activating in the path that the mouse is about to take. And so hippocampal complex could use the top-down connections to activate models in other columns. And that mechanism we already just talked about, but that top-down activation could be based on actual sensory input. That's how we talked about it before. But it could also be based on imagined inputs or imagined movements. And that's kind of visual imagery. So another thing I read is that the activity in the brain from simulated imagery, like when you imagine things, is really similar to activity from the actual sensory input. So it activates, when you think about something, it activates the same regions, same places that activate when you actually see that thing. And so, yeah, in addition, the preplay has been observed in hippocampus and rodents to simulate actions they are about to take, like taking a path to home around an obstacle. And so the idea would be we learn a quick temporary model in the hippocampus of the environment we're currently in, and we can use that to run fast simulations of next actions to take and kind of mentally visualize them using our learned models lower down in the cortex.
This all makes a lot of sense. Go ahead, Jose. I think it was Jose.
No, I was just gonna ask if there's like a concrete example that we can kind of think about when thinking about planning novel actions. Like, I guess it's not really about novel actions as in actions we've never taken before, but we are just given like a new problem, like there's an obstacle.
One thing I was thinking about, or what we talked about before, is like you want to make a cup of coffee in a kitchen you haven't been before, like in an Airbnb or something. And so you quickly build up a temporary model of that kitchen, like where's the coffee maker, where's the fridge, where are the grounds and the filters. And then you can kind of pre-play some actions in the hippocampus of, okay, what would I need to do next in the sequence to figure out kind of the optimal sequence of actions.
Yeah, but we're still applying the same actions that we have learned before. It's just in a different set, different morphology objects. Kind of like if I never knew how to make a coffee and you drop me in an Airbnb, I still wouldn't know how to make a coffee. Like it's I still have the actions of like, okay, I should in general, like I should ground the coffee beans. In general, I should pour some water over it. But like if I never knew that, like we still wouldn't be able to plan these actions, right?
So like I said, a lot of it is also solved by just applying behavior models to new morphologies.
Okay.
I think mostly it's for kind of solving new spatial things, like the coffee mug is in a new, or the coffee pot is in a different location relative to the grounds or
Yeah, it
the
feels
basket
more like
somewhere
tolerance
else.
to spatial deviations and as you say in Hoji, rather than like truly novel actions.
Right. Well, I feel.
Oh,
Jeff.
your audio cut out again,
That
Jeff, for
it's a
a few
novel
seconds.
environment.
Jeff, you got cut off
'cause
after
you
I
can,
feel.
you can take any novel environment and it becomes an environment. I mean, it's just learn it quickly. The important thing I think is the idea is that somehow we have the ability to do this pre-planning. We have the ability to run scenarios as if they were real, but they're not real. But we could run the scenarios that really are real. So to me, it's like you can use the same models. However, imagine all this happening in the hippocampal complex. Imagine I have one behavioral column and one morphology column, just like you showed earlier. And these two, somehow we have to understand how they work together, like you were attempting to do. And now I could say, oh, they can be applied to a situation that I'm familiar with, or it could be applied to one that tied to one that's that I just learned. It seems like the important part is that you have the ability to do it in real and part of the do it in not real.
Yeah.
That which makes me wonder, how do these systems know what's pre-planning and how they know what's real? Is there like, you could imagine these signals are having a different phase, like maybe there's some cycle and like when they're in this part of the phase relative to the background cycle, it's real, or maybe it's a global signal says we're just imagining things now. I don't know.
Yeah, that's exactly the one of the two open questions I wrote down here is who in the cortex knows whether something is simulation or reality. And
I think one thing I find confusing about that is, I think there is like a fairly clear answer from the research, which is that if it's just top down, then it's imagined. Whereas if you get the coupling of top down and bottom up, then it's you perceive it as real. But then I think the confusing thing is normally we've thought of top down as a biasing input. But if neurons aren't actually spiking, how are they representing anything that can be useful for mental simulation and things like that? And so it's like, I think that's if that literature is to be believed, I think that's what I find confusing. Like,
well, you could, but it's a bias, but it's when we talk about top down, like the apical dendrites, they could cause that cell to fire with a different spiking pattern, like a burst versus non-burst. They could cause it to fire on a different period, a different part of a cycle. All bets. I don't think we should restrict ourselves right now. I think we need to work through the mechanics of assuming we know what's real and what's not real. We can work through the mechanics of how these things would interact, and then we could back into like, oh, what's the actual neural mechanism for it?
Yeah, that's kind of what I concluded to is that, it doesn't seem like too hard of a problem. We just don't know the answer right now. But one other possible way could be that when we mentally simulate things, we could still be sending down movement commands, which could then be kind of enough input to elicit activity, but there's still no sensory input to layer 4. But I'm not sure if I just
it's funny when I read. I'm not a slow reader, but I'm not a fast reader either. And what distinguishes apparently really fast readers from someone like myself, when I read, I literally sort of sound out the words in my head, and I almost like I feel like my body's trying to actually say the words. It's like I always wondered, like, is my cortex actually projecting someplace subcortically, and it's just being turned off? It's like it's like I can't. Where like my wife is a super fast reader, and she doesn't do that. She doesn't sound the words. My point is that the point of all that is that the control about turning off, when you might actually be generating the motor commands and it's turned off, prevented externally. It's like dreaming. You might actually be trying to do the behaviors, but it's just subcortically turned off or something.
And I think that's what the literature also says, that if you do like visual imagery, you're just imagining things, the same regions activate as if you see it, but then the like motor projections are inhibited, and yeah, basically turned off. I'll have to find that paper again.
Yeah.
But yeah.
Yeah.
But yeah, I think the bigger problem that I haven't figured out yet is the first open question, which is how would we determine which potential actions to simulate? Like how that still doesn't answer like how can we simulate actions or imagine potential actions and use the learned models we have to figure out which actions we should actually simulate instead of just simulating all possible actions.
Right.
Which, yeah, I don't have an answer to.
Well, this has to get back to the interplay between the morphology column and the behavioral column. Imagine that it could be just those two columns, like you had in that picture. The behavioral column can't be tied to the specific morphology columns. I mean, yes, I know that the stapler has a hinge, but I have to be able to apply hinge to something else. And I think that's what you're saying. Like, how do I know? So that's the crux of the problem here is like, what states am I imagining? Is it a morphology state? Is it a behavioral state? And then how does that imply or suggest a solution? I think it all. Go ahead, Niels.
I was gonna say, isn't it? I think also what you're highlighting, Vivian, is just that part of the issue is the action space. Normally, there's multiple actions you can do. So with a stapler, you can lift it, you can open it, you can close it, you can drop it. I don't know. And most other objects have even more complex action spaces. So it's like, how do you know, if it was like navigating in a maze, like how do you know which direction to go?
So the answer is going to be in the interaction between a morphology column and a behavioral column. It's going to be in there somehow. The morphology behavioral column knows lots of behaviors. The morphology column knows lots of morphologies. And I don't have the answer, but it's in that picture. It's like we just have to draw the lines in the right direction and put the right words on them. The answer will be there. But that's my guess. We're not going to solve it here, so I don't think so.
Yeah. Okay, yeah. So for the sake of time, maybe this was a sufficiently good enough teaser of the idea to think about it further.
Right. What do we want to talk about driving a car while having a conversation or no?
If you guys are up for it.
My family is calling to me, so I have maybe 5 minutes.
Okay. Yeah, it's fine. We don't have to talk about it. You can also read about it and tell me if you have any
Maybe do you want to just describe the problem, and then we can think about it over the holidays?
Yeah, I'll do the problem real quick. So this has bothered me and confused me a lot over the past weeks, and I actually thought of multiple answers and then discarded them again. So I might discard this one too, but it feels a bit better this time. Basically, there are two parts to the problem. One is having the conversation. While we're having the conversation, we have kind of vivid imagery of what we're talking about. We mostly traverse imagined space, like we're not actually like processing physical reality. We're just thinking about what we're talking about, like past events or future plans or more abstract concepts like the relationships between people or politics. And all those can be easily represented and conjure up vivid imagery in our head that has nothing to do with our current movement or sensory input. And so, yeah, I have kind of a proposal for that here. But then the second part of the problem is driving while having the conversation, which is before we said we can only pay attention to one location at a time. And we kind of shift our attention from one location in 3D space to another. And okay, sure, we might be able to pay attention to locations in kind of simulated or mental space as well. But if we're driving a car, we would have to pay attention to two locations at a time, the location in our mental imagined space and the location that we're currently looking at on the road to drive the car and recognize the objects in front of us and the road and all that and the curves. And so, yeah, question is what location in space are we actually paying attention to? And yeah, I wrote down some thoughts here, but there's kind of a high-level picture of what I was proposing is that, yeah, while we're having the conversation, driving is a pre-practiced behavior, so all the kind of necessary model recognition and action outputs are happening here, and there's actually no input to the hippocampus, so we're not actually building a temporary model of the street. We're just driving on autopilot, basically, and what we're paying attention to is the conversation, and that's what's building the kind of mental model and guiding the attention. And then once something unexpected happens here, where we actually need to do some new action planning, then the conversation gets tuned out and we pay attention to what we're seeing and model that and simulate what we need to do about that unexpected event.
I had some, is that it?
Yeah.
I thought about this problem a lot too. I think I have a slight twist difference on it. That you, even while you're driving on autopilot, you have to attend to different things. You look at the signs, you look at the cars, but it's not reaching your hippocampus. It's like you're attending to things, but you're not like forming novel memories of it. You're not forming episodic memories.
What I meant.
But my point is, I think if you think about, imagine this, we've talked about the hippocampus being able to specify, attend to a location in space. What if all columns, all regions can do that? And but they do it just from their point down. So the autopilot driving would also involve a set of attentional states. They start from their point down, V4 down, something like that. And so I'm just saying is I think you do attend to different spaces, but it's in the non-hippocampal part of the cortex. When you see something that doesn't match a model, it's not part of a pre-learned model, then the hippocampus gets involved and you have to attend to it, like you said there. So I think you could have you can have multiple things being attended to at once, but only one at the hippocampus, right?
Yeah.
But if you just imagine the attentional mechanism, whatever the attentional mechanism is, it can occur in any column. And from there on down, it would work.
Okay, yeah, I think that's pretty much how I was thinking of it. I just didn't phrase it as like this is also paying attention to space.
Right.
Since we're looking there, it is, yeah.
Right. That was the one point you missed.
I feel like we kind of I think it's intuitive to talk about a single location in space that we attend to, but I think clearly we have to be able to. It's not that constrained. I mean. Yeah.
Well, I think it would be only one that you'd remember, right?
Because that's what I then wrote down too, is like since the hippocampus is not laying down points for the physical input during the conversation, we will also not learn a model. So we have a hard time recollecting anything from that drive that wasn't out of the ordinary.
Right. So you can imagine.
We do remember the conversation because hippocampus paid attention to it.
You can imagine the top of the neocortex doing everything that the hippocampus does except for laying down quick memories. And so as long as the actions, behaviors, and the states of the objects are all what we've previously learned, then the top of the visual hierarchy can work just like the hippocampus can work. But as soon as something doesn't match, doesn't fit, or doesn't behave correctly, then that propagates up quickly to the hippocampus, and we say, okay, that's everybody. The entire system has to pay attention to this.
When maybe it helps again with the hierarchy, because it feels like at a high level of the hippocampus, you are binding to that point in time, your memory or whatever, that you are in that car, and the fact that you were having a conversation, like those very meta level pieces of information,
right,
in the location of just like where you are in space, because it's not like just because you're having a conversation you suddenly go into some crazy fugue state and you have no memory of where you were when you were having that conversation or anything like that. Like, do you see what I mean? I mean, like, I think it fits with what you started this today with, Jeff, about we have very complex representations that are therefore very kind of parsimonious. They capture a lot.
Yeah.
And And so
Yeah, maybe
yeah.
maybe that can be explained by sometimes you switch your attention to physical space in the hippocampus, and that's then like sometimes when you go back to a location, you remember exactly what you talked about when you walk past there, and maybe that's the kind of episodic memory when you switched attention between the two things.
I think, it may be, we talked about like the idea of conceptual spaces, and lately I've been thinking there is no such thing as a conceptual space. There are physical spaces of which we assign complex objects to, but all conceptual things are modeled as if they were physical spaces. Like I learn things with diagrams. You always talked about, Niels, like the learning of your genealogy, your hierarchical tree of families, whatever, genealogy or whatever. That I picture as an image. It's a picture. It's if I flipped it up sideways or upside down, it wouldn't work as well. So I think it's more like, I'm in the car, I'm talking to you, I'll remember where you sat in the car and whatever. All I'm saying is I don't think we should think about conceptual spaces as somehow different than physical spaces. They're all physical spaces.
Yeah, I wasn't suggesting it being any different. I was just saying your attention is in a different location. It might be your attention is in a physical space, like a memory from the past, or what you're gonna do in the kitchen when you get home.
Okay, that's right. Okay, good.
It's
That's
just
good.
not
Right,
what you're
right.
currently sensing.
All right. Maybe I misheard that, or maybe I misheard something Niels said. I got.
But yeah, it sounds like you actually already thought about this problem and already knew the solution, so I should
Well, I
probably
didn't know. Well, I
talk
don't know if I
about
knew the solution, but I have thought about the problem a lot. So it's like, yeah, right. I think that's. But it's good to remind. What it was good is to remind ourselves that, as I just said a moment ago, the mechanism we're looking for is, say, the hippocampus. For that same mechanism probably could apply starting anywhere in the hierarchy in the cortex, as long as you don't require learning anything new, as long as all the models, the static models we've learned, the permanent models are correct. And so it just is another clue as to how thinking about how the whole system works, right? It's just another clue in that it's not a special mechanism for the hippocampus. The only thing special about the hippocampus is that it can deal with novelty very rapidly, whereas it can form down memories very rapidly.